Today, we're going to continue talking about convergence of series. And we're going to pick up where we left off with the limit comparison test. Last time, we looked at the comparison test, which required us to have a smaller series and a larger series. We had to be able to make the determination that AN is squeezed between BN and 0. So now we're going to refine what we mean when we say one series behaves like another series, like 1 over n squared plus 1 behaves like 1 over n squared, and that's why we're concluding that it converges. Another way we can summarize that is with the limit comparison test. Once again, we need two series because we're making a comparison. Let AN and BN be series, one of which we know converges or diverges. That's a bad way to say this. English is a terrible language for communicating math. One of these is known to be convergent or known to be divergent. We want to make sure that we don't factor out the known, because if we then it says known, convergent, or divergent, it's like, oh yes, every series must converge or diverge. We automatically know if it's convergent or divergent. So one of them we know converges or we know it diverges. One of them is the known series. So running a comparison test means you already know if the series in question converges or not. You already have the answer. These are not tests that you run like a COVID test where you go to the COVID and say, oh man, I hope I don't got COVID. These are tests that you run when you already know what the answer is. But let's think about how it works. If the limit as n goes to infinity of AN over BN is a non-zero constant, then both converge or both diverge. Let's see this in action on the example that we picked up yesterday. When we look at this and we look at the important parts of 1 over n squared minus 1, this looks like 1 over n squared. So in our minds, when we look at this, we immediately conclude this converges. This is like a 1 over n squared. So in our minds, we're thinking this converges. We already know what the answer is. 1 over n squared. The reason that we're concluding this is that we're saying this converges by comparison with 1 over n squared. Then if I take this one level further, 1 over n squared converges because it's a p series with p equal to 2. And 2 is greater than 1, so this is a convergent p series. Not the one in question. 1 over n squared is a convergent p series. And we're saying that 1 over n squared minus 1 converges by comparison. If we want to make a case for this, if we want to prove what's going to happen, if we were taking this to court, this was not just some dumb problem on a math quiz and a court case, we can't use like, oh yes, behaves like 1 over n squared. We can't use the argument, well, that seems reasonable, right? That is never the answer. Never justify something by saying, oh, that seems reasonable. Because we can be convinced of many, many false things. And usually at the root of it is someone saying, oh, that seems reasonable, right? Now you can tell a lot about a person with the bumps on their head. Really, look for the bumps on their head. Tells you a lot about a person. Seems reasonable, right? I mean, no, it doesn't, but for somehow we got convinced of that. Anyway, what are we talking about? So let's use, now we can't use the comparison test, because 1 over n squared minus 1 would be the larger series. The terms here are bigger than 1 over n squared. So we should note that we can't use a comparison test. We're trying to show something converges. We need something bigger that converges. So we can't use the comparison test since the comparison goes in the wrong direction. And in the comparison test, if the smaller series converges, that provides us with no conclusion. If the smaller series diverges, the larger series diverges. If the larger series converges, the smaller series converges. But we get nothing from the smaller series converges or the larger series diverges. Fortunately for our heroes, we have the limit comparison test. So for the limit comparison test, we'll look at the limit as n goes to infinity of an over bn. So 1 over n squared minus 1 over 1 over n squared. We should note that it doesn't matter which one we call an and which one we call bn for the limit comparison test. So let's fix this fraction. This is the limit as n goes to infinity of n squared over n squared minus 1. And as n goes to infinity, n squared over n squared minus 1 goes to 1, which is a non-zero constant. So now we can put our argument together. Since the limit of 1 over n squared minus 1 to 1, as n goes to infinity of 1 over n squared minus 1 over 1 over n squared is equal to 1, which is a non-zero constant. And since the series 1 over n squared converges, the series in question converges by comparison. Since the limit from the limit comparison test is equal to 1, which is a non-zero constant, and since the series to which we are making the comparison, 1 over n squared converges, the series 1 over n squared minus 1 converges by the limit comparison test. So to make this argument, we'd had to pick the 1 over n squared, which means we're picking something that converges, which means we already knew the series 1 over n squared minus 1 converges. The most important part of the problem is looking at the series 1 over n squared minus 1 and identifying this as convergent within the first 5 seconds of looking at it. Since you're new at this, you get 5 seconds to decide. By the end of the week, you'll have 2 seconds to decide. That was the important part of the problem. Keep in mind all the stuff that this means. This means that I'm claiming that the series, the sum, as n goes from 2 to infinity of 1 over n squared minus 1. If I add up all those fractions, I'm getting a finite amount. I didn't say what that finite amount was. I just said that it's equal to some finite amount. And that's what matters. Welcome to the difference between mathematicians and engineers. Engineers are like, oh, how much is it? And mathematicians be like, oh, it's finite. And they're like, oh, yeah, but how much? It's finite. It's more than 0 and less than infinity. Then engineers be like, oh, yeah, I'll do that. And the mathematicians be like, oh, yeah, I can tell. I'm just kidding. No. Mathematicians and engineers don't really talk to each other. Engineers are way too fucking busy, working like 160 hours per week. That leaves you 8 hours to sleep. I don't know what you're complaining about. Of course, that's for the whole week. I mean, there are only 160 8 hours. I had a good friend that was a chemist, and he got an entry-level position at the time, one of, I think it was 5, it might have been 4 companies that would do a particular type of testing. And when I say 4 companies, I mean 4 companies worldwide that would do this kind of testing. Because the testing was very dangerous. So like, at one point when he started working there, he was pretty heavy, and then he went on an exercise program and lost a lot of weight really fast. And they sent him to the doctor. Say, well, we're slightly concerned about this. They go, what? I'm getting healthy, losing weight. They go, we got to make sure. So he went to run some tests. Okay, you have not been exposed to the chemical that's in the lab, so you don't have cancer. You're not dying. You're just losing weight. Go, yeah, that's what I was, because that's how dangerous this stuff was. 4 companies, whole world. Anyway, what were we talking about? I was just on the phone with that guy last night. I don't know why I brought that up. Clearly, it's all starting to go. Oh well. So this part down here, that's not the important part. That's us officially using the limit comparison test to prove that a series converges. But to do this, we already had to know that the series converges. Which is why I use the court case analogy. Because if you're a prosecutor, you don't guess what the answer is and you run a test court case to find out what's going on. You have to already know. At least in math, it is just like yeah or nah. It's not colored by my prejudice or anything like that. You know what I mean? What I'm saying is that the law is really trying hard to be like math, and it's never going to do it. All the lawyers that I see, it's like, oh, couldn't handle math, huh? I'm just kidding, lawyers. Calm down. Jeez. We'll sue. Typical lawyer move. I'm just kidding, lawyers. Calm down. Jeez. I'm not making fun of you because you became a lawyer. I'm just making fun of your math skills. Because you picked lawyer, because it's a very, well, good paying, high ranked profession that doesn't actually require math. See why the law schools are full. I'm just kidding, law schools. Calm down. What's that? Yeah. Incidentally, I think one of the great preparations for law school would be math. It's an axiomatic system, and that's what the law is trying to be. We hold these truths to be self-evident. Those are your axioms. Those like the postulates. You know what I mean? All right. So the reason that I wanted to talk about this a little more. The reason that this test works we're just aiming for some non-zero constant in the limit from the ratio test. What this means is that AN and BN are kind of in balance. They're going to infinity at the same rate. Neither one is winning. If this limit goes to 0, that means the denominator is growing faster than the numerator. It's behaving like a 1 over n, and this is going to 0. So that's not helping us because they're not comparable. We're putting up a little league team against a major league team. The major league team is going to outpace the little league team, and this limit will go to 0. So that would mean Bn is not behaving like An. Bn is winning. And by saying it's a non-zero constant, that's just ruling out the infinite. That would just be the 1 over 0. So if I put the major league team on top and the little league team in the denominator, then this limit is going to go to infinity. I mean, presumably. So that's the idea behind the limit comparison. What this is useful for is not having to make a direct comparison. So for example, if we had a series I don't want to have to analyze this so much just to determine if it converges or diverges. I don't want to have to integrate this for one thing. That sounds awful. I don't want to try to figure out if this is greater than or less than something. I just need an idea of what's going on. And so the only two terms that we had to write down here are the 27 n to the third on the top and 9 n to the sixth on the bottom. That's the only stuff that matters. When n is very large, those are the only two terms that matter. If n is equal to 1 billion, that's nothing compared to the 27 times n to the third. That's 1 billion cubed. This would be 1 billion is a what? Times 10 to the 9th? Sure. 10 to the 9th. This is at times 10 to the 27th. So that it doesn't matter. The dude with the times 10 to the 27th dollars laughs at everybody who calls themselves a billionaire. This is nothing. The only terms that matter when n is large are n cubed on top and n to the 6th on the bottom. So we know right away that this converges. And that's pretty much it. We're done. There's some finite amount this adds up to. First level of detail, This would be by comparison with the series 1 over n cubed. And because of the messy nature of the one that I wrote down, we'd probably use the limit comparison test. So here we are using a limit comparison. When we divide our original series by 1 over n cubed, we multiply the numerator by 1 over n cubed. And so this limit's going to be 3. We're going to look at this as I think this will be okay. So we'll look at this and we'll look at the important parts. N cubed over n to the 6, that's a 1 over n cubed. That converts. The limit comparison test converts. Any questions? So series 1 plus n squared over 1 minus n to the 4th, converges or diverges? That was too slow. Converges. By comparison with what? What's our known convergent series? What are you claiming that this behaves like? Take the biggest term on top, the only important term on top, n squared, over the only important term on the bottom, n to the 4th, and simplify it. N squared over n to the 4th, 1 over n squared. I'm not even worried about the n to the 4th being negative. How about 1 plus n cubed over 1 minus n to the 4th? Converges or diverges? What would you compare it to? And does 1 over n converge or diverge? Right now, we're just trying to build reaction. Here's the way we would do this quiz. I would put 12 series on a page. I would start handing out the quizzes on this side of the room. And once I got to that side of the room, I would just walk back to this side and collect them. That's how fast it needs to go. You need to just identify really quickly whether something converges or diverges. That's what we're aiming for. I should be able to give you a list of 100 series. And you can decide converges or diverges in a matter of minutes. Any questions? I wouldn't do that to you, but that's what I would picture it doing. I don't know if they still do this, where it's called like a mad minute, where you get a paper when you're a kid and you're trying to learn addition and multiplication, and you have to be fast at it for some reason. I don't know why, but you have to be fast at it. And so they just give you this piece of paper, and you're a little kid, so you wait to turn it face down, and a teacher says go, and you turn it over, and there's like 100 problems on the piece of paper, and you just got to add them. There's small things like 7 plus 3 and 8 plus 5, and, you know, like adding single digit numbers. It's all randomly. You have to just write them down. I could not fucking handle that shit. Because it's like, oh, go, and then the timer would start, and I would just freak the fuck out. And I go, right, and I wouldn't be able to do anything. And so I'm like, well, screw this. I'm not going to play your game. When what I was really bad at was pressure. Any questions? So 1 over n diverges. We use the integral test on that one. So it's a p series with p equal to 1. So that's the conclusion that we're going to make. It's p series with p equal to 1, but that doesn't actually answer the question. So I don't want to try to weasel out of it that way. The series 1 over n diverges by the integral test. So we take the integral from 1 to infinity of 1 over x dx. At the very end there, I had a crisis of conscience. I could put equals, even though I spent that whole line plugging infinity in. So I don't know. Here I'm in plugging in infinity. I couldn't bring myself to write equals. My hypocrisy only goes so far. But the integral test is important to remember, not because we want to integrate things, although it's count too. We totally want to integrate things all the time. But especially when they're really nasty rational functions. But it tells us the mechanics of integration tell us where this is going to change, why it changes at 1. Because we have the function 1 over n to the p. If p is more than 1, then adding 1 to it keeps x or the n in the denominator. And so n can go to infinity and that term will go to 0. But if n is less than 1, then when we add 1 to it, it pops the n up into the numerator. And then when x goes to infinity, that term goes to infinity, and so the limit doesn't exist. Is everybody okay? Page 3, man, this convergence stuff. This leads to more notes. I flipped the coin in my mind to decide which test to do next, and it came up ratio test. In the ratio test, we only need one series. We're going to compare a series. Is there an E in absolutely? Absolutely, absolutely, absolutely. This is how they would spell it in like an absolute vodka ad, but there's an E in it, right? This is one of those words that looks wrong no matter how I spell it. That looks wrong. That also looks wrong. It's probably a word that I would trade. It's a word that I would normally trade out, but I can't here because it's a math term and we're stuck with it. But I've just introduced the concept of a different kind of convergence, absolute convergence. Got one more line that we need. I should have given this a name, but there it is. So here's the ratio test. We have a series, and we're going to compare the series to itself. We're going to look at the limit as n goes to infinity of the absolute value of the nth term over the n plus first term. If that limit is less than 1, then we can conclude series is absolutely convergent. If that limit is greater than 1, then the series diverges. This is going to include the case where the limit goes to infinity. If this limit from the ratio test is equal to 1, then the ratio test is not telling you anything. That does not mean that you write no conclusion, because you have to choose converges or diverges. That just means you have to do something else. The ratio test is not the way. The ratio test is like, oh, can't help you, dude. The limit from me is 1. I can't tell. I'm going to refer to this limit as n goes to infinity of the absolute value of an over an plus 1 as the limit from the ratio test. This I call the limit from the ratio test. I have a track record of coming up with very clever names for things. So I call the limit from the ratio test the limit from the ratio test. Pretty awesome, isn't it? A little bit on the nose. So this limit right here is going to be known as the limit from the ratio test. This is because in doing a lot of these tests, we're writing the limit as n goes to infinity a lot. So we've got the limit from the ratio test. We've got the limit from the limit comparison test. We got the limit from the test for divergence. The ratio test is very good when terms have exponential and factorial factors. Oops. The ratio test is very good for series with exponential or factorial factors. The ratio test is blind to rational and radical factors. But this is okay. If we've got rational and radical factors, that's what the limit comparison test is for. The limit comparison test is great at polynomials and radical factors. The ratio test is completely blind to these factors. So this is what we're going to open with tomorrow. We'll talk about the ratio test. 2 things have come up that we need to talk about. 2 open questions. The question of the other kinds of convergence. There's absolute convergence. What's the other kind of convergence? And what's this factorial business? What are factorials? When do they show up? Why would we care? in Game of Thrones fashion, I'm never gonna mention them again. I'm just kidding. We'll talk about the ratio test tomorrow. That's it for today. I'll see y'all on tomorrow. Have a good day and thanks. Bye.